Hi and welcome to this video on moments. The questions that I go through in this video will help you with your revision for your A-level paper 3 maths exam. We're going to look at 3 recent past paper questions, all to do with moments. So starting with this one from 2021, this is a pretty standard ladders type question. And what we need to do first is add all of the forces mentioned in the text to the diagram. So whether they give you the basis for the diagram or not, you should definitely draw one. Reading the information, we're told the beam is in equilibrium up against a smooth vertical wall. It also mentions the coefficient of friction between the ground and the beam. And we're told that the beam is modelled as uniform, which means we can position its weight in the middle. Now I'm going to go through and put each force onto the diagram. First, we've got the weight, which will go directly in the centre of the beam. And then I'm going to mark the floor as rough so that I'll remember. We've also got the reaction forces wherever the beam is touching either the ground or a wall. These always act perpendicular to the surface. I'm going to call these RA and RB for now. I like to draw these dotted lines perpendicular to the beam, just so that when it comes to resolving my forces, I already have the angle indicated that I will need to turn through or away from. Just use the angle that they talk about in the question, in this case theta. So using my knowledge of GCSE angles, I'm marking on anywhere else that a theta appears relevant to each of the 3 forces I've got on my sketch so far. I'm also going to add on my friction, which will be opposing potential motion. The tendency would be for the ladder to slip down and away from the wall, so friction will be acting towards the wall. And since this is in equilibrium, we can say F is less than or equal to mu RA. Right, now we can actually look at what we've been asked to do. We've been asked to show that mu is bigger than equal to a half cot theta. And so we've already with any moments question, I would always recommend you resolve horizontally and vertically first, just because it's super easy and quick to do, and it could score you some marks and become useful later on. So in the vertical, the only force acting upwards is RA, and the only one acting downwards is mg. So since it's in equilibrium, those will be equal. Likewise, for the horizontal, the only force acting to the right is F, and we've just got RB acting to the left. So those will also be equal. Now, I'm choosing to take moments about A, but you could choose to take moments wherever you like. There's no right or wrong answer. A will be the quickest just because I've got 2 forces at A, and wherever you take moments from, you get to ignore those forces. Just a reminder, to take moments, you're investigating the turning force. And so when you turn, the force you're investigating needs to be perpendicular. So in this case, I'm going to make sure mg turns through theta, hence mg cos theta, and then you multiply by the perpendicular distance, which in this case is A. Likewise, do the same for RB. This time, to make it perpendicular, we turn away from the theta, so that will be RB sine theta, and the distance from A is the full length, which in this case is 2A. Set those equal since it's an equilibrium, and the left-hand side is clockwise and the right-hand side is your anti-clockwise. From this, we can cancel the A's. And I know I want a cot theta in my answer, so we can divide both sides by sine theta using our trigonometric identities. I also want mu in our answer, and we do know something about mu in relation to F from our inequality. And so what I'm going to do is use my horizontal to substitute the RB for an F, just so that I now have an F in my answer. Once you've got an F in your answer, we can rearrange to get it on its own and then use the inequality. So rather than F, we can replace this with less than or equal to mu RA. Rearrange, cancel, and there we have the answer. Next, we are told about a horizontal force being applied at A in the direction of the wall. We're also told about tan theta equaling 5/4, and we're given a value for mu. The beam is now in limiting equilibrium, and we need to find the value of K. So there's lots going on here. I'm going to add this horizontal force to the diagram in red, and then I'm going to assume that that is going to change the direction of friction. So friction will now go to the left. So now I need to think about which parts of this question I can keep and which parts I need to do again. So when I did my moments about A, I ignored all of the forces at A, so nothing will actually change there. However, my horizontal resolving will now be different. Furthermore, we're now in limiting equilibrium, so we can use F equals mu r, or in this case, a half Ra. So let's write that one down. I can also write down my new horizontal resolving, Kmg equals Rb plus F. And then finally, I'm going to copy my moments about A from before. This time we know the value of tan, and we can also substitute in rearranged what we got for Rb, Kmg minus F. Now, F equals half Ra, and Ra, the mg's from both sides will cancel. And now all we need to do is substitute in tan theta equals 5/4 and rearrange to get K on its own. Next question is from 2022. Here again we have a uniform rod. I'm going to mark the weight on mg in the middle and remind myself that the length is 2a. We've got a particle attached at C, and again I'm going to mark in those dotted lines which are perpendicular to the rod and include my theta. Distance of C from B will be 0.5a. And since the ground is rough, friction will oppose motion and will act to the right. In this question, we have to explain why friction acts to the right. And this is because friction opposes motion, so we can write that in. Don't forget, we've also got a reaction force at A, which will be acting perpendicular to the surface. Finally, I've also added on my tension in the string, which gets mentioned in part B. Tension acts away from the object. Part B, show that T equals 2mg cos theta. Like before, I'm going to recommend that you do your vertical and horizontal resolving first. So vertically, we've got Ra, and we're also going to have the vertical component of T. So you're going to need to turn T so that it is pointing directly upwards. That will be turning through theta, so we write T cos theta. Set this equal to the downwards forces since we're in equilibrium, mg plus 2mg. We can also do our horizontal resolving as well. F is the only force pointing to the right, and T will also have a horizontal component. This time turn it away from the theta and it will be pointing to the left, T sine theta. Now, looking at these two equations, I don't think we quite have enough to eliminate Ra and F. So we will need to take moments as well. Let's take moments about A, because that way we get to ignore both of the forces there. First force we come across is mg cos theta times A, where A is the distance. Next force is 2mg, same again, turn it through the theta so it's perpendicular and times by the distance. Those two will both be acting clockwise, and then our anti-clockwise force will be tension. Tension is already perpendicular, so you don't need to resolve. Cancel the a's from both sides and rearrange to get t on its own. Given that cos theta equals 3/5, show the magnitude of the vertical force exerted by the ground on the rod at A is. So this is talking about RA. RA we already have in an equation from resolving vertically. So hopefully I can just use this and substitute out T with what we just found in part A. Here I have added the mg's together and substituted in T. Now, cos theta we know equals 3 over 5, and our answer is allowed to be in terms of mg. Finally, part D, we're told about the coefficient of friction being mu, and that the rod is in a limiting equilibrium. Show that mu equals 8 over 19. This means we can use F equals mu r, and F we already have an equation for from resolving horizontally. Substitute in mu RA for F, and then we can use what we found for T in part A. Cancel the mg's, and then find an exact value for sine theta using your special triangle. If cos is 3 over 5, then sine will be 4 over 5, leading us to 8 over 19 as required. Finally, we've got this 2023 question. Again, you can see something very similar to a ladder's question. We've got a rod, we know its maths and length, and we know that it is on rough horizontal ground against a smooth wall. Let's mark all of this on, including reaction forces, although bear in mind it does say in part B that we're going to be calling the reaction force at B S. For part A, we've already answered a question just like this. Since it's in limiting equilibrium, we know F equals mu r. Part B says we can treat the rod as uniform. This question says that we need to take moments about A. So part B, moments about A, remember we get to ignore the forces at A. First force we come across is mg. Turn this through theta so that it's perpendicular. Set this equal to the anti-clockwise force, which is our S, sine theta times the length 2a. Cancel the a's. This time we want cot in our answer, so we'll divide both sides by sine and rearrange to get S on its own. Part C. Given that tan is 3 over 4 and we know the coefficient of friction is mu, find the value of mu. Now let's do our vertical and horizontal resolving if you haven't already. We know that F equals S and we want a mu in our answer, so substitute F into your answer for part B. Substitute in S equals F, and then we can also substitute in using F equals mu RA. Cancel mg on both sides. And if tan theta equals 3 over 4, we know cot theta will equal 4 over 3. Solving this, we get mu equals 2/3. Part D. Find the magnitude of the resultant force acting on the rod at A. So at A, we've got two forces. To find the magnitude, we need to square, add, and square root these forces. RA, we already know, equals mg, so that will be mg squared. And F equals mu RA, where mu is 2/3. So that will be 2/3 mg squared. Simplify this to get your answer. Finally, part E. Now we are told the rod is non-uniform, with its centre of mass closer to B than to A. A new value of S is calculated. We need to work out whether this new value is larger, smaller, or equal to the value of S we already found, giving a reason. So we've been told that this value here of mg moves up here. Let's think about what this would do for our moments about A. It would mean the distance from A is further. So the left-hand side of this would get bigger. And then when you rearrange to find S, your numerator will be bigger. meaning that overall S will be bigger. As a reason, we can write down S will be larger as the moment about A of the weight will also increase. Please comment below which topic you'd like me to do next.